Alright, in this video, what we're going to be taking a look at is curve sketching. Basically, notice I'm using the word sketching and not curve graphing. We're not looking to have a fully complete 100% accurate graph. What we're looking at are just a few key features. Most importantly, where are the zeros? And what kind of zeros are they? Are they singular zeros, meaning they're going to cross over, or are they double zeros, meaning we'll have some kind of bounce going on? And really what we're looking to see is that the general shape of the graph is correct. We're not worried at all about heights or anything else like that. So notice on the axes here, when we're solving a problem like this, there are no indications on the vertical axis what the height is. And that's done intentionally because it really isn't that important. The important thing is that we understand where the zeros are and we understand what's happening within those regions. So first things I want to do is I want to actually find out what the zeros are. Now, nice thing is I've already got this set up ready to go. It's factor. So I can pretty easily find out the zeros. And those are going to be at -4, +1, and +5. Just taking each of those factors and setting them equal to 0 and solving. So I'm going to go ahead and on my graph put a point at -4, at +1, and at +5. We found the zeros at this point, but we haven't done a whole lot more. We want to get a nice view of what the curve should look like. What this has done is essentially set up 4 different regions for us. We've got region 1, 2, 3, and 4. So region 1 and 4 are on the ends, past -4, or to the left of -4, to the right of 5. Region 2 is between -4 and 1, so values in between those two zeros. Region 3 is between 1 and 5, between those two zeros. Our next step then is to find out in each of those regions, are we expecting positive numbers or negative numbers in those? And the way we do this is we're just going to effectively pick any old point that would fit in each of those regions and see if we get a positive or negative value. When I take something in region 1, something less than -4, I might try -5. And I'm going to take -5 and plug it into this original function and only focus on signs, not the actual number. When I plug -5 into this first set of parentheses, I get a -1, so that's a negative sign. And I just wrote the negative, not the -1. When I take -5 and plug it in, I'm going to have -6, so again, another negative number. And when I plug -5 into the last set of parentheses, I'll get another negative number. I don't care about the number so much, but the sign of it. If I take a negative times a negative times a negative, that will end up giving me a negative number. So anything in this region over here should have a negative value. I'm going to then test between -4 and 1. 0 would be a really great one to test. When I plug in 0, I'm going to have 0 plus 4, that's a positive number. 0 minus 1 is a negative number. And 0 minus 5 is a negative number. And so I end up with a positive. Noticing that -4 is a singular root, I would actually expect it to cross over from the negatives into the positives, and it does that. Between 1 and 5, I can pick anything. I'm going to go with 2. Because it's a single root, I'm expecting my answer to be negative. It should cross over because all that stuff in there was positive. Let's see what happens. Plugging 2 in, I'm going to have a positive, positive, and a negative. And so, yep, that does give me a negative value. And so my next step is to take something greater than 5. Let's go with 6. 6 plus 4 is a positive number. 6 minus 1 is a positive. 6 minus 5 is a positive. And I expected it to happen and happened again. I've got a positive. So my sketch of the curve is going to look something like this. So again, I'm in the negative region here, cross over, and I'm positive until I hit that next 0, which makes it negative in region 3, and then positive in region 4. And so my curve looks something like that. This one's a little bit different because now we have those quantities that are squared, and that's going to change a little bit for us. Our zeros, we're still going to follow that same process to calculate them. I've got -6, which turns out actually is a double root, so I'm going to indicate double. -2, which is also a double. And then x minus 4 gives us +4. So I have two double roots and a positive root. I'm going to put those on here. -6, -2, +4. Again, I've got 1, 2, 3, 4 different regions to try. And we're going to do that, and then we'll talk about a quick shortcut we can potentially do, and I've already kind of been hinting at it. So starting left of -6, I'm going to go with -7. Now the nice thing is no matter what I plug into these first two, they're going to end up being positive. A negative squared is a positive squared is a positive. So I don't even need to worry about those first two set of parentheses. I know they'll always be positive. It really comes down to the last one. -7 minus 4 is -11. So I have a negative value. Now again, at -6, I'm expecting it to cross over because that's a 0. So let's plug in -5 and see what happens. So first set of parentheses is positive, second set positive, and x minus 4, -5 minus 4, that's a negative as well. And so it didn't cross, it actually bounced back, which I would actually indicate here with a double root if there's going to be that bounce effect. So it won't cross over, it's just going to hit the x-axis and immediately come back. I wonder if there's a quick way to do this now. So if I'm looking at -2 to 4, a value in that would be 0. So I'm going to have a positive, and a negative. I get a negative again. So anything from here to here gives us a negative value. And then to the right of 4, I'm going to try 5. So I've got a positive, and then 5 minus 4 is 1, so that's a positive number. And I've got a positive solution. And at 4, it did cross over, because that's a singular root. So my graph looks something to this effect. Sorry for the sound effects, just getting into this. So a double root at -6 and a double root at -2, it showed on the graph that we had that bounce here and a bounce here, versus a 4 was a singular root, it crosses over. So that's something to consider when we're doing these questions is if we have a double root, we know it's going to bounce. If we have a single root, then we know it's going to cross over. I wanted to go to, sorry, this. This one's a little different because this one is not set up ready to go. So we're going to potentially have to do some factoring to solve this. So we have x minus 3 times the quantity x squared minus 5x minus 6 times the quantity x squared minus x plus 4. So I definitely know I've got a root here at 3, but x squared minus 5x minus 6, I'm going to see if I can factor that. So I'm looking for two numbers that multiply to -6 but add up to -5. I think that's going to be -6 and +1. And in the last set of parentheses, I'll just bring this down in front of it. There we go. X squared minus x plus 4. I'm looking for two numbers that multiply to 4 and add up to -1. I'm just not seeing them. So I think what I want to do is verify that they're not factorable. So I'm going to find the discriminant here. So taking -1 and squaring it, -4 times 1 times 4 gives me a -15. So what that tells me is that they will be complex roots. I'll be taking the square root of -15. That makes it imaginary. So cool part is when I have complex roots, I actually don't care about these when I graph for our purposes anyway, because we're not at that level that we can actually do anything with those. So I'm going to put a little note here to ignore complex roots when graphing. We just don't care about them. Not that important. So when I graph, I've got my zeros at +3, at +6, and at -1. So if we have singular roots, which is what we're seeing here, that all three of these are one factor, they're not duplicates, then I know at each of those values it's going to cross over. If I have double roots, I know they're going to either bounce back up or bounce back down. So realistically, I don't need to test every single region. I might be able to just test one region and then use that information to kind of figure out the rest. So the easiest thing I can think to plug in would be 0. So when I plug 0 in, I'm going to go to the original function. 0 into here, I'm going to get a negative number. 0 into here also gives me a negative number. And 0 into here gives me a positive. So my end result, f of 0, should be a positive number. I don't know where. I just put it right there because that's a great spot for it. So if I'm looking at that 0, going back, I know that I have to have a crossover because this is not a double root. So I know that at some point my graph is going to go something like that. Probably nicer than that, but anyway. And then past 0, I know that it's going to cross over again at that 3 and have to come back and cross over at 6. Even though I had a fifth degree polynomial, I only had 3 real zeros because the other 2 were complex. And again, I don't worry about those complex zeros when I'm sketching the graph. And so this is my best approximation of what I think a reasonable sketch of the graph would be. Again, it's a reasonable sketch. It's not going to be perfect. It's just going to give us a general idea of what the graph should look like. Find your zeros, plug in points where you need to get an indication of the sign. If it's a singular root, it's going to cross over the x-axis. If it's a double root, it's going to bounce. And from there, we can figure out the shape of the graph.